fluid dynamics. The first thing is terminal velocity. Okay, guys, any idea what terminal velocity is? Terminal velocity?
No, no, I don't know.
Terminal, as the name suggests, terminal means ending, right? So this is the final velocity with which an object hits the ground if it is falling freely. Okay. Meaning, for example, if a parachutist jumps off a plane, what happens? This is the parachutist, for example. So now initially he has a particular weight mg, and because initially there is no air resistance, he's not started moving yet. So that's all the force and that's the maximum acceleration with which he's gonna fall. Acceleration is gonna be the same as acceleration of free fall. Okay. Then as he will start accelerating, the velocity will continue to increase. So will the air resistance. When the air resistance increases, a time will come when the air resistance, now because of this increase in air resistance, this acceleration will start dropping, acceleration of the object, because now there's an acceleration in the opposite direction, which is causing a stop, which is causing the brake, right? There is air resistance. Now, a time will come when the air resistance or the resistive forces become equal to the weight. Why? Because the object will continuously be increasing its velocity, right? Due to the acceleration that is there. So as the velocity increases, air resistance increases side by side. So because of that, the air resistance or the upward resistance becomes equal to the weight. And hence, because both are balanced, the net acceleration becomes zero. And at that point, the object has reached its maximum velocity. Velocity has reached a max. This maximum velocity is called, with which the object is now falling. If no other intervention is added, if nothing else is done, the object is eventually gonna land on Earth with the same velocity, right? That object is gonna hit the ground with the same velocity. This maximum velocity that has been achieved once all forces have been balanced on an object that is falling freely is called the terminal velocity. And this is the final velocity with which an object is gonna hit the ground if no parachute is open, if nothing else happens. Understood? That's terminal velocity. The terminal velocity is the maximum velocity with which an object is going to eventually hit the ground. Understood?
Yes.
Now,
Yes.
how is this relevant to fluids? In fluids, what happens is that we generally have an oil droplet or stuff like that as examples. For example, this is an oil droplet. If it is added into a viscous fluid, now a viscous fluid is always a fluid that has what does viscosity means, guys?
Like the
Viscosity.
thickness of a fluid?
Yeah, thickness, which can be defined as fluid friction, right? It's the friction that the fluid itself has. It's the resistance to the flow of fluid, right? The resistance that the fluid has within itself. That's called viscosity. Correct, Amal?
Yes.
Yeah. So now this viscous fluid means a fluid that has high resistance in it. So when an oil droplet is falling, it has an upward force, upward resistive force acting on it. This is called the drag force, and the weight of the object is the same mg. So when this upward resistive force becomes equal to the weight, that's when the object is falling at a terminal velocity. Understood, guys? Now, this upward drag force can be calculated using a formula called Stokes' law. What is it called? Stokes' law.
Stokes.
Stokes' law is Fd equals 6 pi eta r times v t. That's the formula in which eta, the symbol eta, this is a Greek symbol, I think, or Latin symbol. Whatever this is, this represents a constant to represent viscosity. Okay, this is called viscosity. R is the radius of the droplet, which is falling, and Vt is the terminal velocity that has been attained. Generally, on your exam, you're never asked to solve any calculations using Stokes' law. Okay, but this Stokes' law is generally used to identify the drag force that an object is experiencing. But generally, calculations are not tested from this law. You're just expected to know this equation, and I think this time they've even removed that. Okay, you just know the equation. Now, this is Stokes' law, that's resistance to flow and everything. That's terminal velocity. That's everything about terminal velocity. Understood, guys? Let's move on now. We did fluid drag as well. Fluid drag means the resistive force that acts within fluids towards up in the upwards direction. Now we've got two major types of fluid motion. Okay, fluid can either flow neatly in a single line without causing any turbulence. We call it laminar flow, and this is also called streamline. This one is called non-laminar, also known as turbulent flow. Laminar flow occurs when all the fluid particles are following the same line. Okay, if there are particles flowing, they will be flowing in the same single file. So all particles are flowing straight, neatly, without creating any extra waves, any extra disturbance. Okay, this is called laminar streamline flow. Nonlinear turbulent flow is when there is some sort of obstruction in the pathway, because of which the object is unable to, because of which the fluid is unable to move straight, so it starts creating small whirlpools, okay, or small tornadoes, stuff like this, okay. They don't move in a straight line; they just haphazardly move all around. Okay, because of this, the flow becomes non-laminar, non-linear. This is called turbulent flow. Okay, turbulent flow is generally present almost in all practical situations. Laminar flow is very rarely found. Okay, and how can the laminar convert to turbulent? Well, if fluid is flowing at a certain velocity, and this velocity is increased excessively, so a point will come when this laminar would eventually become turbulent. Okay, so the laminar converts to turbulent when the flow of fluid increases. And this turbulence is generally experienced very significantly in planes. And when person is traveling by aircraft, there are areas of turbulence as well in which you have to fasten your seatbelt um, because of the all the vibrations and stuff, because of the turbulence. So streamline and which is laminar and non-laminar flow. Streamline turbulence. Our equation of continuity. Equation of continuity is based on the law of conservation of mass. This is quite frequently tested as well. Equation of continuity is when you've got a pipe of different diameters, okay, different areas. This is A1, this is A2, for example. Fluid enters here with a certain velocity V1 and exits here with a certain velocity V2. Okay. Now this, like this is V1 and this one is V2. Now equation of continuity is actually a law of conservation of mass. Equation of continuity says The product of area and velocity at the entrance must equal the product of area and velocity at the exit. That's equation of continuity, simple. And if you look at it carefully, area is inversely proportional to velocity according to this relationship. So the bigger and the wider the area, the slower the fluid will flow out. The smaller the area, the faster the fluid is going to flow. Understood, guys?
Yes. Understood.
This is important, okay?
Okay.
And Bernoulli's equation and Bernoulli's effect. Let's look at that. They're saying derivation is required, but in reality, they don't generally test derivation of this Bernoulli's equation at all. Okay.
Okay.
Equation of Bernoulli is given right over here. Pressure plus half rho v squared plus rho gh equals constant, and this is the entire derivation. All of this stuff. You guys can read it. If you understand it, well and good. If you don't, it's fine. You can skip it. Okay, no problem at all. But at least you should be able to identify this equation, and you should know what each and every component of the equation represents. Okay. Example, rho gh is the pressure due to gravity, or we just call it static pressure. P half rho v squared plus rho gh. Where is the P? I remember there was a spelling mistake here. A misprinting mistake, sorry. P represents the total pressure. The feeling it should be added here. Just a second. Let me verify the P. P represents the pressure at that particular level. If the velocity of water within the hose is this much, calculate the pressure within the hose. This is the P. Half rho V squared plus rho GH. Well, rho GH is the static pressure. Half rho V squared is the dynamic pressure. This is the total static plus dynamic. Applications are required. We'll need to read all of this stuff. This part, blood physics is what. Let's see what do they represent. Work done is force times displacement. Okay. This work equals that work. Change in work is okay, fine, this much. Force is the product of pressure and area. Volume is A times X. Now work done is these two minus these two. Now work done is force times area, pressure is total pressure. Okay. Then you can get rid of the stuff here. The potential energy is a constant. P1, the work done in moving the fluid is the sum of the changing kinetic plus potential, whereas P represents the pressure at that level. Pressure within the hose. So water leaves the jet at this velocity and it's at the same level, by the way, not at different levels. So rho GH is going to become 0 because rho GH can only be calculated using when the height difference is there. So height difference is not there. Calculate the pressure P within the hose. Density and everything is given. Atmospheric pressure is also given. Okay. So what does P represent, guys? P represents the pressure that is acted upon the side of the hose. This one is within the hose. This one is the atmospheric pressure. So if we have a horizontal hose right here, one side has atmospheric pressure acting on it and it's exiting with a certain pressure, P, which is inside the hose. Okay. So yeah, one has to be the atmospheric pressure, the other one has to be the internal pressure. It needs to be calculated. Horizontal jet 10 meters per second if the velocity of the water within the hose is 0.4. Calculate the pressure within the hose. Atmospheric pressure is this much. Okay. So we don't have an entry point, there's just an exit from a hose. Now it's leaving. Now there is an atmospheric pressure acting on it. It's P naught, and it's leaving with a certain pressure. This is pressure. Okay, so in Bernoulli's equation, the pressure represents the pressure that is acting at the surface plus rho GH, which is pressure due to change in height plus half rho v squared, the pressure due to velocity. Okay, so this is what the P represents. Okay, guys, just the P means the pressure, the external pressure and the internal pressure. Okay, external pressure is the
Okay.
atmospheric pressure and internal pressure is the pressure of the hose. Yeah, well, again, calculations won't be tested from here. Just this equation is enough. So this P represents the external pressure or the internal pressure. So yeah, with this chapter is wrapped.